Hello everyone, my name's Samuel Barnes. Welcome to the last RRS Live presentation of 2025. This is my presentation on numerical simulations of plasma plume expansion into low-density background gases. And this research is being conducted with Dr. Alexey Volkov in the Department of Mechanical Engineering. So for an overview, when a high-powered laser hits a surface, this causes ablation. So material is removed from the surface. And at lower radiance or energy per area, this causes merely evaporation. But at higher radiance, this causes the formation of plasma and ionization of the ejected material. And this whole ablation process creates a plume of plasma or vapor that is coming up off the surface. So I think this is a good image that illustrates what happens when this laser hits the surface. You get some ejected material, maybe get a plasma plume, and the material itself is melted or damaged. This has many applications, it has many use cases. It's used often in laser machining and welding. It's used in pulsed laser deposition coatings. It's used in spacecraft propulsion. It's used in nuclear fusion lasers, and it's used in some cases in the defense industry. So understanding the ablation plume into the background is important to improve these systems, especially in the cases of things like pulsed laser deposition coatings, where if you have particularly fast particles, they can actually destroy your coating. So this segues into my research question, which is that in low pressure background environments, we observe this plume splitting, where we see fast and slow plumes that are coming off the laser ablated surface. So in this image, you can see if the top of the image is the target and the laser is being shot from below, then we see that there are really two plumes here. There's a fast plume that's coming down and a slow plume that's coming down. And we don't exactly know why this occurs. There's some speculation. There's especially little research when the background density is low but non-negligible. And in order to do this and examine this problem, we need to create a simulation of similar conditions. So we can approximate this using what's called the Riemann problem, which is an initial value problem that has a piecewise constant initial data. So there's only a single discontinuity in this somewhere within your sample. So solutions exist for this problem, not for low density background gas or non-continuum flow. This is similar to the shock tube problem, where it's a 1D example of the Riemann problem where you have two samples of a gas simulated that are separated by a wall, and then at some point this wall is breached or a membrane is broken and the two gases are allowed to mix. However, in our case, it's a lot different because we have an already established initial velocity for the particles on the left of this graph, and we can see combinations of shock and rarefaction waves. So you can see a shock wave, which is a large change in properties over a very short interval, or you can see a rarefaction wave where the properties change over time, over a longer position interval. And in our case, the copper vapor section does have a smaller initial size than the argon background gas. So our method for simulating this expansion is going to be the Direct Simulation Monte Carlo method, which is based on Boltzmann's equations designed to produce the distribution of atoms' velocities due to collisions rather than macroscopic kind of temperature. This describes strongly non-equilibrium gas flows. So in our case, it's useful. This method simulates particles statistically, not deterministically, as is the case with Monte Carlo simulation methods. And it basically compresses a small number of big particles from a big number of small particles. So that means you have to simulate less particles overall, which improves computational efficiency. In addition, it works very well with low-density gases, so the argon background gas we use in our simulations, it works well with that. And one of the best advantages of the Direct Simulation Monte Carlo method is that you can model various effects, such as non-equilibrium effects, rarefaction, and for instance, chemical reactions are very well suited to this. So for our test, we used 1D Direct Simulation Monte Carlo to simulate the plume expansion problem. It was written in C++ and parallelized with MPI, message passing interface, so that multiple cores and multiple nodes can work on the simulation on a supercomputer or high-performance computing center. So we test with a copper vapor expanding into an argon gas. These are the simulation parameters, and we see that the copper vapor has a high initial velocity and a higher temperature and pressure, and the argon background gas has no velocity and a lower temperature and pressure. And these are the simulations, these are the variables within the simulation: the maximum number of particles, maximum number of cells, and the time step and the total simulated length. The simulations were run in two different places. The neutral gas simulations were run on the primary UA-HPC, high performance computing cluster, and it took about 10 hours. The ionized plasma simulations were run on the Alabama Supercomputer Authority's ASA-X supercomputer, and these take over a week, and that is with increased computational power, increased RAM, increased number of processors, and minor changes to the simulation to just make it faster. So these simulations take a long time to run. And here are the results. So as you can see, the particles start at the left and they move over to the right. And what we see is there's initially a high number density of particles on the left side, and then in this kind of shock wave region, we have a very high density of particles, so that we see that large jump there. And then it settles back down to something that's about 100 between 10 and 100 times less particles in the background gas region, simulated particles. So this graph is a comparison of the equilibrium and non-ionized number distributions, and we can see that they're similar but not exactly the same. So we have, there's the same number of particles, I believe, in the wave, but it's this distribution is slightly different. So these are the important simulation test results, where we see that the temperature of the non-ionized plume is a lot higher and a lot more broadly, there's this kind of big fan or wave of the results there, and the equilibrium has a very small temperature rise, at least in comparison to the non-ionized simulation. And the important thing to take note here is that the temperature of the non-ionized gas in the simulation is very high. That's in the 200,000 Kelvin range, which is many times hotter than the surface of the sun. So it's safe to say that we can assume that there's some degree of ionization. So we consider that ionization shows greatly reduced temperatures, and that's in line with our expectations, because we would assume that some of the energy needs to be sent to ionization as opposed to purely temperature. We also, in future work, we need to account for non-equilibrium plasma effects where the different ions and electrons have different temperatures. And in addition, we're going to just, in general, need to do future testing and simulations to identify and predict the causes of plasma plume splitting. So thank you very much for coming to my talk, and I'd like to open the floor to questions.
You mentioned on slide 6 the DSMC method. Are there any other possible simulation methods that you could have used here, or is that the main one that you were looking at?
So the DSMC method is probably the best for our conditions. Technically speaking, you could have used what's called the molecular dynamics method, which is, it essentially simulates every single particle, and it simulates that deterministically and is fully focused on modeling every particle and where it moves and how it collides. But the computational overhead to use that instead of DSMC is much greater, and the results that we get using DSMC are just as good as we would get using that, and takes far less time to run.
I also had a question about the DSMC method. So can that be expanded to more than one dimension, and why is it only in one dimension over 2 or 3? That's
a good question. So yes, the DSMC method can be expanded to all 3 dimensions. It can also, so you can use 1 dimension, 2 dimension. You can have an axially symmetric sort of design. You can have it in 3 dimensions. In our case, 1 dimension is suitable enough for our needs. Really, the plume is not a pure line or cylinder or shape coming out of it. It's almost like a cucumber-shaped plume. But in our cases, I think the plume splitting could be observed even in one dimension, and that gives us good computation. It takes a lot less time to run a one-dimensional simulation than a 2 or 3-dimensional simulation.
I believe you said that collisions in a cell have a certain probability of occurring. How is this probability calculated?
So in DSMC, the probability of a collision, it's calculated by essentially a collisional cross-section. So if you imagine a particle that's moving, it almost creates like a cylindrical-like path as it's moving. And then within cells, you compare the size of this collisional cross-section with the overall size of the cell that you're using, and then that ratio becomes the probability of any collision occurring between two particles within a cell. All right, as there are no more questions, I'd like to thank you all for coming to RRS Live 2025, and roll tide.